Analyze the successive ionization energies for element X. The energy required to remove each successive electron from an atom of element X is given as follows. First ionization energy, i.e., 730 kilojoules per mole. Second ionization energy, i.e. 1450 kilojoules per mole. Third ionization energy, i.e. 7700 kilojoules per mole. Fourth ionization energy, i.e. 10,500 kilojoules per mole. Identify the core chemical barrier, the jump, in ionization energy. The energy required to remove the second electron, 1450 kilojoules per mole, is roughly double the first, 730 kilojoules per mole, which is a typical increase due to removing an electron from a now positively charged ion. However, there is a massive five-fold jump in energy between the second and third ionization energies, 1450 kilojoules per mole to 7,700 kilojoules per mole. This huge jump indicates that the third electron must be removed from a stable, inner shell core orbital, closer to the nucleus, experiencing a much stronger effective nuclear charge after all valence electrons have been removed. Determine the valence configuration and common ion charge of X. Because only 2 electrons can be removed relatively easily before encountering the inner shell barrier, element X must have exactly 2 valence electrons. To achieve a stable noble gas configuration, element X will lose these 2 valence electrons, forming a cation with a +2 charge, X to the power 2+. Determine the ion charge of phosphorus, P. Phosphorus is located in group 15 of the periodic table. Elements in group 15 possess 5 valence electrons and typically gain 3 electrons to complete their octet. Therefore, in an ionic compound, phosphorus forms a phosphide anion with a -3 charge, P to the power 3. Balance the charges to find the empirical formula. To form a neutral ionic compound, the total positive charge from the X to the power 2+ cations must balance the total negative charge from the P to the power 3 anions. The least common multiple of 2 and 3 is 6. 3x to the power 2+ ions provide a total charge of 3 times, +2, equals +6. 2p to the power 3 ions provide a total charge of 2 times, -3, equals -6. Combining these in a 3:2 ratio yields the empirical formula X3p2, which identifies option C as the correct answer. The correct answer is option C, X3p2.